Chapter 2, Motion, Part 2. The question now before us is force. And the question is, what is a force? And how do we describe it relative to other quantities that we have already considered? So, a force is any influence that can cause an object to be accelerated. Recall, in part 1, we study at great length the acceleration, which is a vector, which implies that there is a change in the velocity. So what causes a change in velocity? It must be a force. So therefore, the acceleration is what registered the change in velocity. So there's a force that's related to the acceleration that is causing the change in velocity. An object then is accelerated if there is a net force, that is an unbalanced force. So you will find that force and acceleration go hand in hand. You cannot have one without the other. A net force, N-E-T force, which is the resultant force. So if there is a resultant force acting on a body, that body will experience an acceleration, which means it will experience a change in its velocity. See, so those three go together: force, acceleration, change in velocity. Okay, let's go on. Now, Newton, you will find, has three laws of motion. So we'll start with the third law, and then we will work backwards to get the first and the second. The third law, when an object exerts a force on a second object, the second object exerts an equal force on the opposite in the opposite direction on the first. So when one object exerts a force on a second object, the second object exerts a force, equal force, in the opposite direction on the first. So forces like this come in pairs. For every action of one kind, there's an equal and opposite reaction of the other kind. Like, I am sitting on my chair and I'm pushing down on my chair because gravity is pulling me down. But at the same time, the force of the chair is pushing upward on me. If the force were not pushing up on me, I would literally plummet through the chair. Okay. So action, reaction. This is an illustration of this. This young man pushed the table in one direction, and the table passively pushed back on him in the other direction. And so if he's on a frictionless surface, this is an ice surface he's on. If the table sails one way, you will find that he will have an equal and opposite motion in the other direction. And an illustration of this is this. Let's watch this, please. So what he's showing here, there are horizontal forces. Obviously, there's a weight force that's not talked about in this presentation. So action and reaction forces, an object, an other way of stating Newton's third law of motion, for every action there's an equal and opposite reaction. The action and reaction forces always balance if there is no net force. Okay, so here's another situation. One young man is pushing to the left, the other is pushing to the right. This block will not move if they are pushing with equal and opposite forces in the horizontal direction. So the vertical motion is not considered here. Just horizontally, this is a balanced situation. Now Newton's second law of motion, which will later you will see is going to be written in terms of a mathematical equation. Newton's second law of motion states the net force on an object equals to the product of the mass and the acceleration of that object. It's a time, and here means time. So we will be able to write an equation that Newton discovered, and it'll be a simple mathematical equation relating mass, acceleration, and net force. And here it is here. Newton's second law in algebraic form. F for force, M for mass, A for acceleration. I've said to you when you have the juxtaposition of two quantities in this manner, M and A in this case, it means that they multiply with each other. A mass times an acceleration gives a quantity that we will call force. Now, in order to really understand what force is, we need to also have a unit for force, and that's going to come up in a moment. So mass may be thought of as a quantity of matter, and the SI unit of mass is the kilogram. We've already said that. So now come to force. All right. So the SI unit of force is named after Newton, Newton, and we just use capital N to have this derived unit. So we say 1 Newton, then, when you have 1 kilogram and it's experiencing an acceleration of 1 meter per second squared, there must be a force of 1 Newton acting on that 1 kilogram. So hear me again. 1 Newton acting on 1 kilogram will cause an acceleration of 1 meter per second squared. So in the context that we're speaking of, we generally think that the force is the cause, the acceleration is the response to that cause. We also talk about a unit of force in the British system, that is the pound, and 1 pound is equal to 4.45 newtons. Okay, so we will go back and forth between those units. We can convert between a pound and a newton. In fact, your weight, if you weigh something like 160 pounds, you can then convert your weight from pounds to newton. If you multiply 4.45 by your weight, that will give you your weight in newtons. Here is another illustration of what we just said about the relationship between acceleration and force. Now back to the first part of this chapter where we use this mathematical equation to find the acceleration. So we're going to do that. And then we're going to find what must be the force to produce such an acceleration. Find the force needed to serve a 60-gram tennis ball at 30 meters per second. Serve means to impact. The ball is in contact with the racket for no more than 0.005 seconds. So we can easily calculate the acceleration. It's Vf minus Vi over t, so which is 30 meters per second divided by the time. So the acceleration is 6,000 meters per second squared. Now we're going to use that in the next slide. So we bring that now over. Now we can use this formula here, and we can juxtapose and calculate 60 grams times 6,000 meters per second squared. Before you multiply, you have to change grams to kilograms. So 60 grams is 0.06 kilogram. You multiply and you get 360 newtons. That's in round figures probably about 200 pounds. Okay, let's go on. Now, we also have weight is another type force. It is the force due to gravity. So the weight in the object is the force with which gravity pulls it towards the center of the earth. And we use the formula now as opposed to saying F equals mg, we say W equals mg, weight, mass, and g is acceleration of gravity. So when it comes to gravity, a is already known. We call it G. It is 9.80 meters per second squared at the surface of the Earth. It gets smaller and smaller as you move higher and higher, farther away from the center of the Earth. But on the surface, it's 9.80 meters per second squared, 9.80 kilograms per, I'm sorry, 9.80 newtons per kilogram. Let's see now. And let me just go on from there. So what is the weight of a 5 kilogram mass? We can calculate that right there, and it's 4.9 newtons. Another example of weight. Newton's first law then. The first law states, if no net force acts on it, an object at rest will remain at rest, and an object in motion remain in motion at constant velocity. The first law is also called the law of inertia. So that's Newton's three laws there. I need you to learn those three laws. Inertia then is the apparent resistance of an object offers to any change in its state of rest. And this is Newton's law, this is his equation expressing the gravitational attraction between any two bodies. F is equal to some constant capital G. This is not the acceleration due to gravity. The mass of the first body times the mass of the second body divided by the distance between the two bodies squared. Okay. And so here's an illustration of the force of gravity between the Earth and the Moon. And that force is needed to keep the Moon in orbit around the Earth. The gravitational force is in existence there. Now, if you know the value of G, which we do, you can use that then in order to calculate the mass of the Earth, and that will be shown in the next slide. Well, first we show you that as you move farther and farther from the center of the Earth, here you're about 6,400 uh, kilometers from the center of the Earth. Your weight is about 600 newtons. As you move farther and farther out, your weight gets smaller and smaller, but it doesn't go to zero. It never goes to zero. Okay. So this is way then you can calculate the mass of the Earth. The mass of the Earth is given here as g times the radius of the Earth squared divided by the gravitational constant. And this is what you get here for the mass of the Earth. And it was Newton using this algebra was the first person to calculate the weight of the Earth, or the mass of the Earth. Lastly, I just want to mention to you that there is needed to be a certain speed at a certain point in order to leave the Earth gravitational field or the gravitational attraction. An object can be launched in space here, but for it to finally have this kind of orbit and escape from the Earth, it has to have a certain speed at its lowest point there. Okay, that's all I wanted to present on this section, and that takes me to the end of this portion. Bye bye now.